Some machines carry the weight of their creation long after the men who built them are gone. They run through history, trailing the ambitions and the obsessions of those who designed them, moving through time with a kind of mechanical indifference to the human cost of their existence. But there are rarer machines so entangled with the fate of their creators that the two stories become impossible to separate. Machines where the line between triumph and tragedy runs directly through the same moment, the same decision, the same single point where genius and catastrophe met and became permanently inseparable. This is the story of one of those machines, a locomotive that its inventor gave everything to build, that repaid that devotion in the worst possible way, and that afterward vanished so completely from history that for decades most people doubted it had ever existed at all. The story begins not in a workshop or a railway yard, but in a hospital ward in the industrial city of Manchester in the winter of 1901. A man named Arthur Coleridge Drummond lay in a bed surrounded by the kind of institutional stillness that settles over places where people go to recover from things that can't be recovered from. He was 43 years old, which, in the context of Victorian and Edwardian engineering, meant he was at the absolute peak of his professional life. The best work, by conventional measures, should have been ahead of him. Instead, he was lying in a hospital bed with injuries that would keep him there for 8 months. Injuries sustained not in some industrial accident or railway disaster, but in the testing of a machine that he himself had designed, that he had spent 11 years of his life building, and that had, on its first full-speed trial, demonstrated in the most brutal possible way that it was not yet ready for the world. Drummond was not a well-known figure in the railway world. He had spent his career at the margins of the industry, working as a consultant rather than as the chief engineer of any major company, taking contracts where he could find them, surviving on the income generated by smaller projects while devoting his real attention and his own financial resources to the machine that consumed him. That machine was a locomotive that he called, with the kind of quiet confidence that sometimes borders on arrogance, the perfect engine. The name was not accidental. Drummond genuinely believed that the history of locomotive design had been a long progression of approximations, each generation of engineers getting closer to an ideal that nobody had yet achieved. The ideal he had in mind was specific and technical. He wanted a locomotive that wasted nothing, a machine where every unit of heat generated by the combustion of fuel was converted through a sequence of mechanical processes that he had spent years calculating and refining into tractive effort at the wheel. No steam exhausted before its full energy was extracted. No heat lost to the atmosphere through leakage or inefficient insulation. No mechanical energy absorbed by friction in systems that weren't contributing directly to forward motion. This was not an impossible dream in theoretical terms. Thermodynamically, the ideal engine Drummond envisioned was coherent. The problem was engineering it into a machine that could actually run on railways. The gap between thermodynamic theory and mechanical reality was precisely the gap that had defeated every previous attempt to build a truly efficient steam locomotive. Drummond was convinced that his predecessors had failed not because the goal was unachievable, but because they hadn't been willing to depart radically enough from conventional design approaches. He was willing to depart radically. He was, if anything, too willing. The design that Drummond developed over 11 years of calculations, drawings, revisions, and more revisions was unlike anything that had appeared in British locomotive history. The boiler was a compound water tube design, borrowing principles from marine engineering that had never been applied to a railway locomotive. Instead of the conventional arrangement of fire tubes passing through water, Drummond's boiler used water tubes passing through the hot gas stream, a configuration that allowed much higher operating pressures than conventional designs could safely achieve. The working pressure was specified at 400 pounds per square inch, nearly double the standard for express passenger engines of the era. The steam circuit was correspondingly complex. Steam generated in the high-pressure boiler passed first through a high-pressure cylinder where it did the majority of its work. It was then collected, reheated to restore the temperature lost during expansion, and passed through an intermediate cylinder. From there it was collected again, reheated once more, and passed through a large low-pressure cylinder where the remaining energy was extracted before the steam was finally condensed and returned as water to the boiler. This triple expansion arrangement with intermediate reheating was theoretically elegant and practically nightmarish. The number of pipes, valves, heat exchangers, and control mechanisms required to make it function was extraordinary. The locomotive's internal systems were more complex than anything that had previously been attempted in railway engineering anywhere in the world. Drummond financed the construction partly through his own savings, partly through loans, and partly through contributions from a small group of investors who believed in his vision with an intensity that, in retrospect, looks more like faith than engineering judgment. The construction took place at a small workshop in Sheffield, where a workforce of 7 skilled craftsmen worked under Drummond's direct supervision for 3 years. The standards he demanded were extraordinary. Components were machined to tolerances that the workshop's equipment could barely achieve. Assembly procedures were documented with a precision that was decades ahead of common practice. By the autumn of 1900, the locomotive was complete. It sat in the Sheffield workshop gleaming with fresh paint and polish, its complex internal systems invisible behind a conventional exterior that gave no hint of the mechanical revolution that Drummond believed it represented. It looked, to the casual observer, like a reasonably conventional express locomotive of its era. Only the density of pipework visible at certain angles suggested that something unusual was happening inside its carefully crafted skin. The initial tests were conducted at low speed on a short stretch of private track near the workshop. These tests went well, encouragingly well. The locomotive moved under its own power. The complex steam circuit functioned as designed. The pressures and temperatures at various points in the system corresponded to Drummond's theoretical predictions with a closeness that made him dizzy with satisfaction. The years of calculation, the months of construction, the financial strain, and the professional isolation all seemed, in those initial moments of successful operation, to have been entirely justified. The problem was that low-speed tests on private track could not reveal the locomotive's behavior under the conditions for which it had been designed. The perfect engine, as Drummond's complex reheating system made clear, needed to be running hard to demonstrate its advantages. At low speeds, with light loads and moderate steam demands, the sophisticated triple expansion circuit was largely irrelevant. Its benefits would only appear when the locomotive was operating at full output, when the pressure differences between the stages were large and the heat recovery systems were working at full capacity. To properly evaluate the design, a full-speed trial was essential. Drummond arranged this trial with characteristic thoroughness. He secured permission to use a section of the Great Central Railway for a high-speed run. He selected a stretch of relatively flat track where the locomotive could be brought up to maximum speed without the complication of gradients. He assembled a party of observers, including 2 engineers whose opinions he respected and whose testimony he intended to use when presenting the perfect engine to railway company executives who might be interested in licensing the design. He prepared measuring instruments to record pressures, temperatures, and fuel consumption throughout the run. On the morning of the trial, the atmosphere was tense with anticipation. Drummond drove the locomotive himself, something that was unusual but not unprecedented for an inventor demonstrating his creation. His fireman was a young man named George Parkin, chosen for his skill and his calmness under pressure. The observers rode in a special coach attached behind the locomotive. Everything was in order. Everything was as prepared as it possibly could be. The run began well. The locomotive accelerated smoothly, the complex steam circuit working exactly as Drummond had designed it. Speed built gradually, passing 40 miles per hour, then 50, then 60. The observers in the coach behind were recording data, noting with growing interest that the fuel consumption figures being calculated were genuinely impressive, significantly better than contemporary express locomotives of equivalent power output. Drummond, on the footplate, was experiencing the extraordinary satisfaction of seeing years of theoretical work validated by physical reality. Then, at approximately 70 miles per hour, something changed. The change was subtle at first, a slight variation in the sound of the exhaust that Drummond registered in the back of his mind without immediately understanding its significance. Then a pressure gauge on the complex manifold that connected the intermediate and low-pressure sections of the steam circuit began to show readings that diverged from the predicted values. Drummond reached for the regulator, intending to make a minor adjustment to the steam supply to the intermediate reheater. What happened next happened very quickly. The adjustment Drummond made triggered a pressure transient in the intermediate steam circuit, a sudden spike that the system had not been designed to handle because the theoretical calculations had not fully accounted for certain dynamic effects that only manifested at high speed under real operating conditions. The pressure spike propagated through the circuit faster than Drummond could respond. A connection joint in the high-pressure steam piping, stressed by 11 years of occasional test operation, failed suddenly and completely. The steam release was explosive in its intensity. At 400 pounds per square inch, steam contains energy that expresses itself with violence when suddenly freed. The cab of the locomotive was immediately engulfed in scalding vapor. George Parkin, the fireman, was thrown clear by the force of the release and sustained burns that took months to heal but did not threaten his life. Drummond was not so fortunate. He was directly in the path of the high-pressure steam jet and sustained burns across much of his upper body that were severe enough to require immediate hospitalization, and that left permanent damage that would affect his health for the rest of his life. The locomotive itself survived the incident in better condition than its creator. The steam release had been dramatic, but the mechanical damage was limited. The failed joint could theoretically be repaired. The system could be inspected and modified, and the perfect engine could potentially run again. Whether it would be wise to run it again was a very different question, and one that Drummond was in no condition to consider from his hospital bed. During the 8 months of his recovery, the locomotive sat in a railway siding in Lincolnshire, where it had been moved after the incident. Its future was uncertain. Drummond's investors, shaken by the accident, were reassessing their commitment. The railway companies that had been potential customers received news of the failed trial with reactions ranging from cautious concern to barely concealed satisfaction at the failure of an unconventional approach that many of them had always regarded with skepticism. The engineering press, which had occasionally published speculative pieces about Drummond's project, now published pieces that were noticeably less speculative and noticeably more critical. Drummond emerged from hospital in the autumn of 1902, diminished in body but undiminished in conviction. He was still certain that the perfect engine represented a genuine advance. He attributed the accident not to any fundamental flaw in the design, but to a manufacturing deficiency in the specific joint that had failed. A deficiency that could be corrected, a lesson that could be incorporated into a revised design. He returned to Sheffield and began work on what he called the corrections, a program of modifications that he believed would address every vulnerability that the trial had exposed. The problem was money. The accident had consumed the confidence of his investors along with much of the remaining financial reserve. One by one they withdrew their support, each departure politely worded, and each departure another blow to a project that was already financially precarious. Drummond sold his house. He moved into lodgings. He reduced his personal expenditure to the absolute minimum while continuing to pay the workshop staff who were implementing his modifications. The determination was absolute, and the resources were disappearing. By 1905, with the modifications nearly complete but the financial situation critical, Drummond made a decision that he believed represented his last real chance to save the project. He wrote to every major British railway company requesting an opportunity to demonstrate the locomotive. He wrote to the Board of Trade. He wrote to engineering institutions. He wrote to wealthy industrialists whose names appeared in the financial press. He received polite rejections, non-committal responses, and silence in roughly equal proportions. The one positive response came from an unexpected direction. A consortium of South American railway investors, seeking modern technology for a new Highland Railway they were planning in Colombia, expressed genuine interest. They were not deterred by the accident history, perhaps because they were less familiar with it, or perhaps because their own project was ambitious enough that they were attracted to rather than repelled by unconventional approaches. Negotiations began in late 1905 and continued for nearly a year. In the end, the negotiations failed, not because the South Americans lost interest, but because Drummond's health collapsed before a final agreement could be reached. The injuries from the 1901 accident had left a legacy that his doctors had warned him about, but that he had chosen to ignore in favor of continuing his work. In the winter of 1906, he was hospitalized again, and this time the prognosis was severe. He died in March of 1907 at the age of 49, with the perfect engine undemonstrated, the modifications complete but untested, and the financial situation of the project catastrophically unsustainable. The aftermath was swift and depressing. The workshop was closed. The staff dispersed to other employment. The investors, such as they remained, moved to liquidate whatever assets could be recovered from the project. The locomotive itself was sold for a sum that represented a painful fraction of what it had cost to build to a small railway contractor who intended to use it for light freight work on a private industrial line in the north of England. For approximately 4 years, it served in this role, running in conditions very different from anything Drummond had intended. Operated by crews who had no knowledge of its history or its sophisticated internal systems, and who maintained it according to generic steam locomotive practices that were entirely inadequate for a machine of its complexity. The triple expansion circuit gradually fell out of proper operation as components wore without appropriate attention. The high-pressure boiler, maintained at lower pressures than its design intended, developed leaks that were addressed with patches rather than proper repair. Slowly, systematically, through neglect rather than any dramatic failure, the perfect engine ceased to be perfect. Its final documented appearance in any railway record was in 1911, when a maintenance ledger from the industrial railway that had purchased it recorded an inspection finding that described the locomotive as uneconomical to repair and recommending withdrawal from service. After that entry, nothing. The trail goes cold with the completeness that only pre-bureaucratic record-keeping can produce. There are no scrapping records, no transfer documents, no subsequent mentions in any source that researchers have been able to identify. What happened to the perfect engine is genuinely unknown. The most probable explanation, supported by circumstantial evidence gathered by railway historians in the latter half of the 20th century, is that it was scrapped in approximately 1912 or 1913. Its sophisticated components melted down and recycled without anyone present understanding what they were destroying. But this is inference rather than documented fact. There are those who believe, or who want to believe, that the locomotive may have survived in some form, perhaps stored in an agricultural building, perhaps buried beneath decades of accumulated debris at the site of some long-closed industrial facility. These beliefs are almost certainly romantic rather than historically grounded, but they persist because the perfect engine was exactly the kind of machine that inspires the unwillingness to accept that it is simply gone. The design work that Drummond produced, the engineering notebooks and calculation sheets that survived among the papers disposed of after his death and were eventually acquired by a technical library in Leeds, reveal a mind of genuine brilliance operating at the absolute frontier of what was technically conceivable in the early 20th century. Engineers who have studied those notebooks in the decades since their discovery have reached conclusions that carry a particular kind of sadness. The basic thermodynamic approach that Drummond pursued was sound. The principles he was applying were correct. The efficiency gains he was theorizing were real and potentially achievable. Where he failed was not in the concept, but in the execution, specifically in the management of dynamic pressure transients in a high-pressure compound steam circuit, a problem that the mechanical engineering of his era lacked the theoretical tools to fully analyze and the manufacturing technology to fully solve. In other words, Drummond was right, but he was right in a world that wasn't yet equipped to prove him right. The perfect engine needed materials that wouldn't exist for another generation, manufacturing tolerances that would require machine tools that were still decades from development, control systems that would only become possible with technologies that Drummond couldn't have imagined. He was, like so many inventors, whose stories end in tragedy rather than triumph, precisely right at the wrong moment in history. The locomotive that killed its inventor and then disappeared has no memorial. There is no preserved example in any museum. There is no heritage railway that runs a restored version of the machine. There is only the Leeds notebook collection, those dense pages of calculations and sketches that represent the life's work of a man who gave everything to an idea and received in return a ruined body and an early death. Drummond's story is not unique in the history of technology. The annals of engineering are full of men and women who pursued correct ideas at the wrong moment, who paid personal prices that no professional achievement could justify, who disappeared into history while the ideas they championed eventually found their vindication in forms they would never recognize. What makes Drummond's story distinctive is the particular intimacy of the connection between the inventor and the machine that failed him. The perfect engine didn't just fail as a technical demonstration. It physically destroyed the man who built it, burned away years of his life, and then outlasted him just long enough to fade into the kind of obscurity that feels, in retrospect, like a final insult. Some machines carry the weight of their creation. Some machines carry the weight of their creator's destruction. The perfect engine did both, and then it vanished, leaving behind only those notebooks and leads, and the quiet, persistent question of what might have been if one connection joint had held, if one pressure spike had been absorbed rather than catastrophically released, if one morning's trial had gone differently on a stretch of flat track in Lincolnshire in the autumn of 1900. The answer to that question is unknowable, but the asking of it is a form of tribute to a man who believed, with a conviction that cost him everything, that perfection was not just a theoretical possibility but an engineering obligation. Arthur Coleridge Drummond was wrong about a great many things, but about that, he was absolutely right. And the locomotive that bore his vision, however briefly and however catastrophically, was the most honest expression of that belief that the physical world ever produced. It ran once, it nearly destroyed itself and its creator in the same moment. And then it disappeared, as completely as if it had never existed at all, leaving only the echo of what it might have meant if the world had been different, if the time had been right, if the perfect engine had found the perfect moment to prove that it truly was what its maker always insisted it was. Perfect.